So, yeah, word embeddings. Most probably, actually, how many of you have you ever heard about word2vec or used word2vec? Awesome. Glove? Really? fastText? Oh my God. StarSpace? Only me and Facebook, I guess. Okay, cool. Word2vec and all these techniques are essentially, like, they belong to the category we call word embeddings. So essentially, they're doing the same thing. They're mapping words from a vocabulary to a dimensional space. And they have a very, very nice property and feature, whereas they capture semantic similarities in the d-dimensional vector space. So we can actually compare vectors and see how close they are in that space. And there are other properties that follow that, like word analogies, like if you get the vector of the word king, subtract the vector of the word man, you add the vector of the word woman, what you'll be getting is something really, really close to the word queen. So, like, yeah. And that's completely unsupervised in the sense that we just throw the algorithm like in millions of, like hundreds of millions of rows of words, and we're getting back this representation plus whatever comes along. So we'll be discussing a little bit not only word2vec, but all the other techniques and their, how they're set up and how they're working a little bit. And then we'll be discussing what can we actually do around them. So, OK, cool. Typical representation seems like that. So you have like a machine, and you're mapping, like you have a word, and you're mapping the word in a d-dimensional vector space. So, for example, this comes from Glove 200-dimensional models, where the whole machine is mapped to the sequence of numbers, and the word details and to that sequence of numbers. Since they are essentially vectors, you can get cosine similarity between them, find the angle, and see how similar they are in the vector space, right? Which is very, very useful. There are several very nice packages, especially in Python out there, for actually doing like semantic similarities and so on. So Glove is implemented, word2vec are implemented in the package gensim, which is awesome. So if you get a trained model, load the vectors or train a model, and you query what's the word, most similar word to car, given your corpus, you can get different results. But in this example, we see that car is very closely related to driver, race, grass, and so on and so forth, and tax, and so on and so forth. All these associations are learned without supervision, just from raw text, which is fantastic. It's awesome. This is essentially the architecture of word2vec. So it comes in two. It's the other way around, sorry. Oh. Yeah, that's correct. There are two models in word2vec introduced by Mikolov at some point 2013. And essentially, it's a probabilistic neural language model. So language model is when we have like a sequence of words, and we want to find the probability of the word following that sequence of words. This is exactly what they're doing, but there is a very, very nice byproduct of this training procedure, whereas we're getting a matrix, size the number of words in the vocabulary by the number of dimensions we want, and this is our embeddings. This is our word representation. It comes in two flavors. The first one is the SIBO model, where we're trying to predict the word given the context of a fixed size context. So you have like 5 words, and we're trying to predict the 6th. And also comes in skipogram model, which is somehow reversed. So we try to predict the context given the word. Training is done like usually with some variation of stochastic gradient descent. There are nice hacks around that, especially when we have huge vocabularies. And we'll be talking a little bit later on that in the details. Then we have Glove. Globe followed, I think it was 1 year later, word2vec. It's a completely different approach. Instead of trying to predict the next word given a sequence of words, we're doing a kind of like slightly different approach. So we're building a Cooccurrence matrix. So we have, say, a corpus with some like vocabulary of size V, and we're building a Cooccurrence matrix of word I and word J appearing in the same context, fixed same context of, say, again, 5 or 10 words. And then, given some mathematical mumbo-jumbo, which I won't get into too many details, but we can actually follow that later, we're formulating this objective function where WIs and WJs are the word vectors, which we sum together eventually to get the word embeddings representations. The BIs, BJs are biases, and XIs are essentially the Cooccurrence matrix. We formulate the entire objective over the vocabulary as least squares problems. We minimize that, and we're getting our representations back. It performs roughly equally to word2vec. To be honest, it's a little bit much faster to train, but also it's a little bit difficult when you have like huge vocabularies because you have to first build the entire Cooccurrence matrix. So you have to do 2 passes over at least your vocabulary, your corpus essentially. Then here comes fastText, or bag of tricks for text classification. I have all the links and related material and references at the end of the slides, so you can actually follow that. It's very similar to word2vec, but also learns some bindings of character level n-grams. So we have a word, we're representing the word as a bag of characters. We're learning embeddings for each of the n-gram of this bag of characters. And then we average everything together. So a word is the embedding for the word is the average of the entire bag. This has the very, very nice feature that we can actually learn embeddings for very similar words, like misspellings in search engines. It's massively useful. You're already using that in Argos, actually, to try to find like spelling errors and so on and so forth. It's extremely fast because, again, it shares some common implementation with and ideas with word2vec, and also very nice features about like hashing and so on and so forth. And recently, like it was like 4 or 5 months ago, Facebook Research published StarSpace, which is kind of like a generalization of like embedding techniques. Just like a stop here, both fastText and StarSpace are not only used to learn embeddings, like to output embeddings, given words produce the mappings. There are several other functionality that follows these techniques, but I won't step into the details here because actually it's like you don't have the time, but you can learn like link association, graph associations, do classification, and so on and so forth. I recommend you have a look. It's massively interesting what happens there. So in StarSpace, we're having like, again, a corpus or like generally entities, and we're formulating an objective function where L is the cost function, similarity, a similarity function. The cost function can be softmax or hinge loss or something like that. And we're essentially giving the algorithm one positive pair of some notion and a bunch of negative examples. If you're familiar with word2vec, there is a thing called negative sampling. So imagine that we can have potentially hundreds of millions of words in a vocabulary. The last layer in the network is a softmax layer. So we need to compute probabilities for hundreds of millions of words. That's not efficient, right? So one of the workarounds introduced by Mikolov back in 2013 to make it faster is that just keep the word we know in advance because we're scanning the corpus, and instead of computing the softmax in the entire vocabulary, just pick randomly keywords, right? This is called negative sounding. It's proven to be very, very efficient. Now we're talking about efficiency. There is a very, very interesting approach of how the optimization is done, which is called asynchronous stochastic gradient descent. So essentially what happens is that we have X threads in the implementation doing optimization. And we don't even care. We don't do any kind of like locking or anything. We don't even care if we overwrite same like cells in a matrix or like rows and stuff, because if eventually we have like a huge vocabulary and we wouldn't want it doesn't matter eventually. So we're making like stochastic like gradient descent updates like in parallel. So that's one of the techniques that's used both in, actually in every algorithm, fastText, word2vec, and so on. Okay, so, we have word embeddings. What do we do with that? One straightforward approach, especially if you don't really want to go on like deep learning space. So, you have pre-trained a pre-trained model, just download it from somewhere, or you just build your own model. I mean, you don't really want to go into the deep learning space, but you just want to feed your algorithm, your logistic regression, your support vector machines with features, or even with just a typical neural net at some points. So most of the times you have a text, like a collection of words, and some classes, and you want to build a classifier on top of that. So, like, for example, sentiment analysis, right? There are various ways to do feature engineering around that, given the fact that the logistic regression support vector machines are expecting fixed size of vectors as an input. So one typical way to do that is, like, especially for short text, just get the representations of all the words per document and average them. Just feed it to the algorithm. There are some other workarounds or like interesting approaches. So you can have like bands again of words and the matrix they produce of embeddings, and get the max per dimension, the minimum, standard deviation, normalized means, and so on and so forth. There is also a very, very interesting technique which is also introduced like a couple of years ago, which is called smooth inverse frequency, where essentially for every word in your collection or sentence, you're getting all the representations. You're formulating a matrix based on like weighted averages of word frequencies, and then you're doing PCA and you're keeping the first principal component, which is fantastic, like conceptually, and works pretty well. But if you still, actually, yeah, where it works pretty well. We found out that it works really, really well, this technique, on metaphor detection. So we have like documents, and we want to classify a sentence if it's a metaphor or not. So the way we're doing it is like learn embeddings from the corpus, and then we have a labeled set of tagged documents where we know sentences, essentially, where we know which of them are metaphors, which of them are literals. Get the verb in that sentence, get a window, a context window of size, usually 3 or 5 or something like that. Average the embeddings, feed that to a classifier, support vector machine or logistic regression, and we get, like for Greek, for the Greek language, we get something like 8% accuracy, which is state of the art. It's very good results, essentially. I'm not sure if you're familiar, but metaphor detection is one of the most hard problems to solve in NLP. Also, just again, statement, there is no such thing as AI. We'll never get there in our generation. Don't just buy what people are selling. But still, if you want to get to the deep learning world, and you don't really have to wait to train your embeddings models, you can use pre-computed vectors directly in your model. So this is how to do it, like, for example, with Keras. So you're setting up, among other layers, you're setting up an embedding layer, and you're loading like the word matrix, which is essentially, again, like all the words in your vocabulary. You're feeding that to the embedding layer like when you're setting up the model, and you're making it not trainable. So you have pre-computed embedding layers from any model you like. It can be fastText, it can be word2vec, it can be Glove, it can be anything. And given, again, the problem, different problems might have different response, like in terms of accuracy, with different models, right? For most of the experiments I've been doing for, say, for example, author schema attribution, word2vec and fastText tend to be much more efficient than Glove. fastText is, like I said, very, very useful in cases where you have like spell checking errors and you don't really want to throw away low frequency, like low up frequency terms in your vocabulary, because they matter. If a user types something like misspelling something like in your search engine, you still need to keep this word and just try to infer what he's searching for, and so on and so forth. Before we get to the questions, how much time we have? Oh, okay, we have like 20 minutes. Let's also have some fun with some math. Okay, this is Glove. You remember this one from before? The Cooccurrence matrix, biases, weights, and so on and so forth. There is also one interesting component in this function as well. It's a function of the Cooccurrence matrix, where essentially we're kind of like trying to smooth a bit the effect of very frequent words. So we're dividing with x max, like raised to the power, like x over x max to the power of a, where typically a is like 3 over 4, and x max is something like 100, and so on and so forth. This is the heuristics that came out from the team that built Glove, and they work pretty well. Again, StarSpace. Okay, there are some very interesting properties of embedding models, and namely why they work. We don't really know. There is a very, very interesting work in this paper, which again is yet another embeddings model, which I won't even go into details because it's random walks and it's like super complicated, and I don't know that well. That's the truth. But the idea is that it's kind of like approximating this like very slow random walk over discourse topics. So we're in a position where we're generating text. The embeddings models are treated as a generative process, and with very, very slow, like a small probability, we're changing topics. So that explains some very interesting features why this works in like high dimensional space, like the mapping and the mapping, semantic properties. A very interesting other property, another property which is very, very, very interesting, is that relatively small dimensions work better. So if you train a model with, like, say, 500 dimensions and train another with, like, 1,000, even like in million words, most of the times the smaller, like the most compressed model will perform better, which is very weird, right? So you have like a huge matrix of cooccurrence and stuff like that. So you're applying essentially like a huge level of compression, and the lower you go, like at least for like in the range of like 100 to 500, you're getting better results. If you increase this dimensionality to 1,000, 5,000, so on and so forth, the model still works, of course, but not that well, which is weird. All these properties of like getting continuous representations of words, started like several years back from LSA and so on and so forth. And people were observing very weird properties, like, say, for example, if we get, again, the Cooccurrence, whatever, matrix, instead of feeding, like, for example, to PCA, the matrix, like the counts, if we just take the logs of the square roots of the counts, it worked better. But try to explain that to a linguist. Okay, so yeah, I mean, there are very, very interesting things going on there. We still just don't really know why they're performing that well. So yeah, that's pretty much it. If you have like any other questions around embeddings and stuff, please go ahead.
How language dependent are those results you were talking about?
Sorry?
How language dependent are those results? Like you saying it works better with log of square root, for example. Is that language specific, or do you know if it carries through?
All these are kind of like language independent. You can actually, like the word, for example, king minus man plus woman, it works in at least 2 languages I know of, like Greek and English, of course.
Thanks. How do you evaluate an embedding technique? How do you decide which one to use?
That depends on the case. Say, for example, you have the word analogies case. So you have like a vocabulary as an input, and you're trying to find the best analogies. And then you have like perfect matches. So king minus man plus woman equals queen, that's a perfect match. So if you have princess, it's not a perfect match, but then you can be like relax a little bit your metrics, like your accuracy function, say something like top K, top 5. So if the word you're after is on the top 5 most similar to the word you're getting, yeah, consider that like a positive match. There is also actually, like, if you're training models and you're fitting the features, the embeddings to classifiers, to do other stuff, the accuracy of the final model. So for the metaphor detection case, this is exactly what we've been working with. We're training several dimensional models, fitting that to the classifier, getting the overall accuracy of the classifier, and we found out that, again, the best dimension was something like on 450, something like that.
Yes, you didn't seem to offer any opinion about this approach.
We won't hear it.
You didn't seem to offer any opinion about what approach works best. So do you think level?
I think I mentioned at some point it's kind of like problem dependent, I guess. So, and there's also a trade-off between the size of the vocabulary, computing power. All these techniques are working also, like, awesomely well, like on a, like my home computer is like 32 gigabytes RAM, 8 cores machine, like 5 years machine, and it works like most of the models are trained like in 2 or 3 hours. StarSpace is slow. We've been discussing that a little bit with Fox that created in Facebook. It's completely different in some certain aspects from like other models, so that can explain why it's been slower. But for typically same configuration parameters like cutoff words, how many words you expect to see in your corpus, to start training and so on and so forth, plus dimensions and so on, fastText is much faster, and word2vec is also much faster. For Glove, most of the times the training procedure is much faster, but you have to scan the entire vocabulary to build the Cooccurrence matrix. And for huge vocabularies, that might take time or explode your memory. It's like memory bounded. Depends.
You mentioned training a classifier for metaphors in Greek, and you said that it has an accuracy of 80%. Mm-hmm. How many classes did you have in your problem?
2.
Like, so metaphor or non-metaphor?
Metaphor or non-metaphor.
And what was the percentage of each one of them? Was like 50-50?
Roughly 50-50.
Okay. Thank you.
there's a follow-up paper presented in, I think it's 10th of May in Spain with this work exactly. So it's going to be like somewhere in the wild in a bit.
I think we have another question in the other corner.
Yeah, so sorry, this is a bit of a basic question. So I'm just kind of trying to get my head around it. So are you basically, do you have a model where you feed in words and it gives you vectors attached to each word?
Yeah, exactly. You're absolutely right. That's a very, very good question. Why do we need that in the first place? I didn't mention that, and that's, yeah, my bad. Imagine that you have like a vocabulary of, say, like 1 million words. That can happen like in a huge corpus, right? And you want to maybe encode this information and feed it to a neural net. So one hot encoding will be having 1 million vector, like size vector. That's certainly not a good way to go from like an efficiency perspective. So you want to somehow compress this information, but still maintain something very useful. Also, if you get this one hot representations, all the words are equally spaced in that space. So the word, I don't know, like cake and the word tank will be similar to the word bear and the word star, right? You don't get any information of that. But if you compress all this information and you produce continuous representation of these words, then words like king, prince, and so on will be very, very close to the space. Words like cake and so on will be, like, again, very close. And you're getting something out of it. Your algorithm, your machine learning model learns to understand which words are closely together semantically, which is very, very important. OK, thanks.
Specifically in Argos, what kind of problems? So you mentioned, say, your spelling errors or something you're dealing with. What kind of things are you doing to?
So a vocabulary is something like entities like in a set of symbols, right? So for example, consider the case that instead of like natural language processing, you have again a fixed vocabulary of product IDs. And you have sessions where a user sees products, like product 1, product 2, product 3. Group all that by session, get all the sessions, and you have essential text. Feed that to an algorithm, and you're getting the best similarity model of products, like in a collaborative filtering fashion you could ever have, for example.
When you deal with your vocabulary, how do you deal with, take an example, how do you deal with branded terms, like Apple, Samsung? Do you put weights on your feature afterwards?
The question was, how do we deal with branded terms, like in Argos? And actually, it's work in progress. I have a very good colleague looking exactly at that, because we're trying to predict intention of the queries. And one of the models, like I said, we've been trying is fastText, which seems to be working very, very well. Follow up on that in like a next meetup or something.
Ciao. Maybe repeat the question.
On a sort of related note, can you combine these sort of techniques with ontologies, to sort of like the main ontologies around sort of brand names and product names?
The question was, can we blend these techniques with ontologies? Which actually, I'm not sure. I haven't seen that, and I don't really like ontologies. So, but most probably yes. I mean, if have a look, or even build some like a classifier on top of that. Most probably this is doable, but I haven't done it myself, so I don't know.
When you train your model,
Hear that.
sorry, when you train your model, do you prefer use Argos data itself to train the whole embedding, or you prefer to somewhere else as a embedding?
For like Argos specific tasks, or like we've been doing.
Yeah, for example, you train a model for your Argos product category. Do you use Amazon as well?
No. Just our own clickstream, because we need to infer what people like our customers believe product similarity is, not different.
is your best practice or recommendation here?
Sorry?
Is this your best practice?
There are several algorithms we are using in recommendations, but that's also one.
Okay.
Essentially, just to give you a better kind of a description around that, every retail business has two major problems to solve from a machine learning point of view. The first one is product similarity, or similarity in general, how similar stores are, how similar products are, and so on and so forth. And the second is kind of a little bit more involved, is price elasticity of demand, which again is related because products that are similar will tend to have the same elasticity of demand, meaning that if you adjust the price a bit, you will expect to see different response of demand. So there are clusters groups there. So things we've been trying to actually learn product similarities or similarities in general that can be very useful for things like recommendations, demand forecasting. For example, I'm trying to forecast, I'm supply chain in Argos. We're trying to forecast products. Every 6 months, we change 1/3 of our product base, of our catalogs. We have completely new products. We know nothing about those products, and we still need to forecast them. So our best guess is to find most similar products and use some machine learning mambo jumbo there to get forecast. Thanks.
You were talking about this optimized dimensions for the embedding. Did you ever check if it depends on the corpus? If you were to give it a corpus of 12 teenager-year-old literature against all corpus of literature, does it change this dimension?
Very, very, very nice question again. Yeah, it's totally corpus dependent in the sense that, for example, there have been really nice, a couple of papers in the literature where human bias is projected in embeddings. Whereas, for example, gender bias, where men are associated to engineers and women are associated with house stuff that learned from corpora from ages ago or something like that. Or there is a very, very nice example where some guys were trying to build sentiment analysis algorithm based on word embeddings, and turned out that Mexican restaurants were classified as bad because the word Mexican was used in a bad way in this corpus. So you have to be very, very careful because your data, that's a very, very good question, actually. Your data is not what you think it is, it's what it is.
We have time for a couple more questions. Are there any more questions?
Okay, can we just solve the equation now? No? Okay, cool. Thanks very much.
Okay.